Hello everyone. Today we're going to talk about a symmetric encryption algorithm, that is, the Advanced Encryption Standard. This lecture mainly introduces encryption and decryption, AES operation mode, data format, padding, and interrupt control, and finally gives some example codes. Let's start with an introduction to encryption. There are two primary types of encryption, symmetric and asymmetric. The symmetric methods include AES, triple DES, and SM4, Chinese State Cryptography Administration, and the asymmetric methods include the commonly used RSA and ECC, elliptical curve cryptography. The symmetric cryptography uses the same cryptographic key to both encrypt and decrypt data. Therefore, such key should be shared through a secure channel in advance. It has fast instruction cycle and is suitable for handling bulk data. The asymmetric cryptography uses asymmetric keys to encrypt and decrypt data. It is complex and slow in encryption or decryption process, and comparatively less efficient in handling bulk data. In practical, the symmetric and asymmetric methods are combined for better performance. That is, asymmetric encryption is used for keys exchange used for symmetric encryption, and symmetric encryption is used to encrypt messages in the follow-up. As shown in the block diagram of AES used in AT32 MCUs, input data and output data are swappable. AES has four operation modes, that is, encrypt, key scheduling, decrypt, key schedule, plus decrypt. The key length can be 128, 192, 256-bit. AES supports chaining modes, including ECB, CBC, CTR, GCM, GMAC, and CCM. AES provides complete and error status flags and the interrupt bits to enable the corresponding interrupt. The AES, Advanced Encryption Standard, in AT32 MCUs has the below features: support 128, 192, 256 bits of key lengths, corresponding to 10, 12, 14 rounds of encryption, respectively. Support multiple operation modes, including ECB, CBC, CTR, GCM, and CCM. Support forward initialization vector, IV. Support data transfer through DMA with two channels, that is, DMA access. Support input or output data swapping in half-word, byte, and bit. Support encryption or decryption interrupt or resume in groups with software. The next part introduces some operation chaining mode supported by AES. Electronic Codebook (ECB) is the most basic chaining mode, which is enabled by setting CHN equals 0 in the AES underline control register to perform encryption or decryption. In ECB mode, messages are divided into 128-bit blocks for encryption or decryption independently, which means that the encryption or decryption of each block is independent. If one encrypted block is less than 128 bits, it should be padded to reach 128-bit length. In conclusion, ECB supports parallel operation with simple encryption and fast processing. However, it has one critical shortcoming, that is, identical plaintext blocks result in identical ciphertext blocks. As shown above, the left one is the original image and the right one is the encrypted image using ECB mode. The right figure remains the outline of the original image, reflecting that the identical plaintext blocks result in identical ciphertext blocks. To avoid the shortcomings of ECB mode, the cipher block chaining (CBC) mode is recommended. In CBC mode, the plaintext is divided into blocks, and then the current plaintext block is XORed with the previous ciphertext before encryption, so that the identical plaintext blocks do not result in identical ciphertext blocks. To guarantee the uniqueness of the plaintext, an initialization vector, IV, is used on the first block to replace the previous ciphertext. Decryption is performed in a similar way. Compared with ECB mode, in CBC mode, the encryption of each plaintext block depends on the previous encryption, which means that CBC mode do not support parallel operation, but supports chaining encryption only. Therefore, the CBC mode is comparatively less efficient than ECB mode. The counter mode, CTR, takes into account the advantages of both ECB and CBC. CTR mode has the below main features in comparison with CBC. First, Encryption and decryption of blocks can be done parallelly, since such operations only depend on the keystream block generated by a nonce and an incremented counter. Second, incorrect ciphertext affects only the corresponding bits in plaintext, and the encryption and decryption of other blocks are not affected. In CTR mode, encryption and decryption are performed with the stream cipher. A nonce and an incremented counter are combined to create a keystream block that is XORed with the plaintext to produce ciphertext. Decryption is essentially the same as encryption thanks to the symmetry of the XOR operation. Users can select ECB, CBC, or CTR mode for encryption and decryption to guarantee data integrity and authenticity in case of any error or attack to the communication link. Message authentication is necessary. The purposes of message authentication are: locate the data modification if any, check data integrity with a hash function, guarantee data authenticity by using a hash function and a secret key. GMAC, Galloy Counter Mode. MAC is a type of message authentication code MAC used in cryptographic communications. It uses GHASH to calculate the message authentication code, that is, MAC value. GMAC generates tag data only for message authentication, instead of encrypting or decrypting data. It is recommended to use Galloy or Counter Mode GCM to encrypt data and verify data integrity, as well as guarantee message confidentiality and integrity. The GCM mode combines the counter mode CTR of block cipher encryption with the Galloy mode of authentication GMAC. In GCM mode, data encryption and decryption are completed in counter mode. The encrypted data and additional authentication data are combined into a block and then calculated with the GHASH function to generate a tag. The additional authentication data is not encrypted, but should be verified for authenticity by the receiver, including IP address, port, and initialization vector, etc. As shown in this GCM block diagram, the blue dotted box includes programs in counter mode, and the red dotted box includes programs of GMAC. In addition to GCM, the CCM counter with CBCMAC is also applicable to guarantee data confidentiality and integrity. The GCM mode combines CTR counter mode and CBCMAC cipher blockchaining message authentication code. In GCM mode, data encryption and decryption are completed in counter mode. The encrypted data and additional authentication data are combined into a block and then calculated with the CBCMAC to generate a tag. This is the CCM block diagram. Similar to GCM mode, the blue dotted box includes programs in counter mode, and red dotted box includes programs of CBCMAC. We've discussed about AES and its commonly used operation chaining modes. Let's talk about AES data format. According to NIST FIPS Pub 197, AES encrypts and decrypts data in blocks of 128 bits for words/32 bits and performs operation for each word on a two-dimensional array of bytes. The data in AES encrypt or decrypt core unit is in little-endian format. Plaintext and ciphertext in AES-related registers are in the formats as shown in this figure. This figure shows the formats of key and initialization vectors in AES-related registers. As aforementioned, input data and output data can be swapped to meet data storage format requirement in different applications. AES encrypt or decrypt core unit supports swapping of plaintext and ciphertext by half-word, byte, or bit. Setting the SWP bit in the AES underline control register to set for swapping methods, as shown in this figure. Setting the SWP to process data in big-endian format. Let's move on to the padding. As aforementioned, plaintext is divided into 128-bit blocks for computation. Data blocks are input in order through the AES input data register and wait for the complete flag assertion. Then, data blocks are output through the AES output data register. This process is called padding. Padding can be performed by CPU or DMA. CPU performs padding with polling flag bit or receive interrupt. Follow the below steps. Step 1. Set PDIE equals 1 and RWEIE equals 1 in the AES underline control register to select receive interrupt method. Step 2. Configure the AES control register AES underline control AES key register AES underline keys and AES initialization vector register AES underline IFX, and then set the AES EN bit in the AES underline control register to enable AES. Step 3. CPU accesses AES input data register AES underline IDT for 4 times and input a data block in order. Step 4. Wait until the AES encrypt or decrypt core unit completes computation, depending on the control process. For padding control with polling flag bit, CPU accesses AES underline STS register repeatedly until the PDFS bit is set. For padding control with interrupt, after an interrupt is received, CPU accesses the AES underline STS register to confirm that the PDFS bit is set. Step 5. In the encryption or decryption process in chaining mode, CPU accesses the AES output data register AES underline ODT for 4 times to get the processing result. If it is the additional authentication data with GCM and CCM, skip this step. Step 6. Write 1 to the PDFC bit in the AES underline FCLR register to clear the PDFS bit. Step 7. If the to-be encrypted data is larger than 16 bytes, that is, more than 1 data block, repeat steps 3 to 7. Step 8. If the to-be encrypted data is less than 16 bytes, pad the data with 0 to a complete data block. For encryption or decryption with the FCM and CCM, configure the NDD number of dummy data bit in the AES underline control register and set the LST bit according to the number of 0 padding. Step 9. Wait until the AES encrypt or decrypt core unit completes computation, identical with Step 4. Step 10. If the NDD bit in the AES underline control register is configured, CPU accesses the AES underline STS register to confirm that the NZDFS bit is set. Step 11. In the encryption or decryption process in chaining mode, CPU accesses the AES output data register AES underline ODT for 4 times to get the processing result. If it is the additional authentication data with GCM and CCM, skip this step. Step 12. Write 1 to the PDFC and NZDFC bits in the AES underline FCLR register to clear the PDFS and NZDFS bits, and then reset AES-EN. Padding with DMA method allows data transfers without consuming CPU resources. Follow the below steps. First, if the to-be encrypted data is not a multiple of 16 bytes, pad the data at the end with 0 to a complete data block. Second, configure 2 DMA controllers and then enable. One DMA controller gets data from memory and then fill into the AES underline IDT register. Another DMA controller gets processing result from the AES underline ODT register and then write into memory. Note, for encryption or decryption in GCM or CCM mode and the to-be encrypted data is not a multiple of 16 bytes, the DMA length setting should deduct the last block. The last block processing is executed in the next stage. Third, set DMA-WE equals 1 and DMA-RE equals 1 in the AES underline control register to enable DMA write channel and read channel. Fourth, set PDIE equals 1 and RWEIE equals 1 in the AES underline control register to enable encrypt or decrypt processing done interrupt and write or read error interrupt. Fifth, configure the AES control register AES underline control AES key register AES underline keys and AES initialization vector register AES underline IFX, and then set the AES-EN bit in the AES underline control register to enable AES. Sixth, after AES is enabled, data transfer is automatically completed by DMA controllers and AES without the intervention of users. After padding is done, AES encrypt or decrypt core unit will set the PDFS bit in the AES underline STS register and send an interrupt to CPU. 7th. Write 1 to the PDF-C bit in the AES _FCLR register to clear the PDFS bit, and then reset AES-EN. In chaining mode with ongoing padding process, AES encrypt or decrypt core unit AES can suspend encryption or decryption of data blocks to suspend and record the current task and release resources for tasks with higher priority. The above figure shows the task suspension and resume process. Padding suspension and resume can be done by DMA or CPU. This slide gives the padding suspension and resume procedures. Unless otherwise specified, these steps are identical for both DMA and CPU methods. Next is the interrupt control. AES interrupt control is simple, and the interrupt can be triggered by PDFS, refs, or WEFS. These 3 status flags have their separate flag clear bit. In addition, the NZDFS bit is used to record the block with non-zero dummy data processed in GCM or CCM mode. This flag does not trigger any interrupt. Next, we'll give some example codes of AES. Take CCM mode as an example. We need to prepare the initialization vector, key, and additional data. Enable AES clock and call the CCM encrypt or decrypt processing function in the main function. Firstly, initialize AES structure in the CCM encrypt or decrypt processing function. For CPU operations, the CCM encrypt or decrypt processing function is used to write and read data blocks one by one. For DMA operations, enable DMA read or write to access data from a specified address instead of writing or reading data one by one. After AES processing is done, disable DMA. Summary. To sum up, AES in AT32 MCU series, firstly, its common operation modes include ECB, short for Electronic Codebook, is simple, high-speed but less secure. CBC, short for cipher block chaining, is secure but does not support encryptions in parallel. CTR, short for counter mode, is highly secure and support encryptions in parallel. GCM, short for Galloy or counter mode, is highly secure with message authentication. CCM, short for counter with CBCMAC, is highly secure with message authentication. Secondly, AES data format, encrypt or decrypt data blocks of 128 bits. Operate on two-dimensional array of bytes. Data is in little-endian format, and swapping of input and output data is support. Finally, padding, it can be done by CPU or DMA. It can be suspended and resumed by CPU or DMA. That's all for today's lecture. Thank you.